In this section, we discuss the ideal gas law. An ideal gas is an idealized model for real gases that have sufficiently low densities. The condition of low density means that the molecules of the gas are so far apart that they do not interact except during collisions that are effectively elastic. The ideal gas law expresses the relationship between the absolute pressure, the Kelvin temperature, the volume, and the number of moles of the gas. In Chapter 12, we have already explained the relationship between the absolute pressure and the Kelvin temperature of a low-density gas when we discussed the concept of absolute zero. A small amount of gas is put into a container that has a constant volume. Since the density is low, the gas behaves as an ideal gas. Experiment reveals that a plot of gas pressure versus temperature is a straight line that can be extrapolated through absolute zero. The graph indicates that the absolute pressure, P, is directly proportional to the Kelvin temperature, T, for a fixed volume and a fixed number of molecules. The relation between the absolute pressure and the number of molecules of an ideal gas is easy to see. Experience indicates that it is possible to increase the pressure of a gas by adding more molecules. This is exactly what happens when a tire is pumped up. When the volume and temperature of a low-density gas are kept constant, doubling the number of molecules doubles the pressure. Thus, the absolute pressure of an ideal gas at constant temperature and constant volume is proportional to the number of molecules, or, equivalently, to the number of moles of the gas. To see how the absolute pressure of a gas depends on the volume, consider a piston filled with a gas. When the piston is in the upper position, it is easy to move downward. However, when the piston is in the low position, at a reduced volume, it is more difficult to move further downward. Many of us have experienced this when pumping up a bicycle tire using a manual pump when the tire is nearly full. The pump handle is easier to push at the top of the stroke and more difficult at the bottom, where the pump cylinder's volume has been reduced. Thus, it is possible to increase the pressure of a gas by reducing its volume, and if the number of molecules and temperature are kept constant, the absolute pressure of an ideal gas is inversely proportional to its volume, V. The three relations just discussed for the absolute pressure of an ideal gas can be expressed as a single proportionality. P is proportional to Nt divided by V. This proportionality can be written as an equation by inserting a proportionality constant R called the universal gas constant. Experiments have shown that R equals 8.31 joules per mole times Kelvin for any real gas with a density sufficiently low to ensure ideal gas behavior. The resulting equation is called the ideal gas law, which is stated as follows. The absolute pressure, P, of an ideal gas is directly proportional to the Kelvin temperature, T, and the number of moles, N, and is inversely proportional to the volume, V. In other words, PV equals nRT, where R is the universal gas constant and has a value of 8.31 joules per mole times Kelvin. Note that the temperature must be in kelvins in this equation. Sometimes it's convenient to express the ideal gas law in terms of the total number of particles instead of the number of moles. To obtain such an expression, we multiply and divide the right side of the equation by Avogadro's number, Na equals 6.022 times 10 to the 23rd particles per mole, and recognize that the product, N times Na, is equal to the total number of particles given by uppercase N. The ideal gas law can then be written as PV equals nKT, where R divided by Na is defined as K, called Boltzmann's constant, and has the value K equals 1.38 times 10 to the negative 23 joules per Kelvin. Suppose that, in some problem, we are given 3 of the 4 parameters in the ideal gas law for a gas under constant conditions and in equilibrium. We can always solve for the unknown variable. For example, what is the volume of 1 mole of an ideal gas at standard temperature and pressure, or STP? First, we need to know what is meant by standard temperature and pressure. In order to reproduce conditions and to compare the way things operate, from electronic gadgets to gases, we need to know how they behave under identical conditions. One common set of environmental conditions is standard temperature and pressure, or STP. In this case, the temperature is set to 273 Kelvin, or 0 degrees Celsius, which is the freezing point of water, and the pressure is equal to 1.013 times 10 to the 5th Pascal, which is 1 atmosphere, and the average air pressure at sea level. In our case, when we solve the ideal gas law for the volume and substitute the SDP conditions, we have V equals nRT divided by P, which is equal to 1 mole times 8.31 joules per mole times Kelvin times 273 Kelvin divided by 1.013 times 10 to the 5th Pascal. The mole and Kelvin units cancel, and we are left with 0.022 joules per Pascal, which reduces to meters cubed, which is a volume, as it should be. Converting, we find that 1 mole of any ideal gas at standard temperature and pressure occupies a volume of 22.4 liters. Suppose the parameters of a gas change from some initial state to some final state. The ideal gas law applies in both cases, and we can write PV divided by nRT initial equals PV divided by nRT final. Consider the special case in which the volume and pressure of an ideal gas are allowed to change, but the number of moles and the temperature T are held constant. We first write our equation with the indices distributed to the individual variables. Next, since the initial number of moles equals the final number of moles, and the initial temperature is equal to the final temperature, they cancel along with the constant R on both sides. We are left with the initial pressure times the initial volume equal to the final pressure times the final volume, which is known as Boyle's law. A pressure-volume plot for a gas at constant temperature is called an isotherm. We see that the pressure is proportional to 1 over the volume for a given temperature. Isotherms for T equal 100 K and 300 K are shown. We can now do the same thing as we did to obtain Boyle's law, but this time hold the pressure and the number of moles constant. Canceling the constant variables, we obtain another special case of the ideal gas law for constant pressure and a constant number of moles. The initial volume divided by the initial temperature is equal to the final volume divided by the final temperature, and this is called Charles' law. In summary, the ideal gas law is a model for real gases that have low densities. Low densities in this case means that the molecules are so far apart that they don't interact. The ideal gas law is given by PV equals nRT equals nKT, where the lowercase n refers to the number of moles of the gas, and the uppercase N is the number of particles in the gas. R and K are constants. Finally, standard temperature and pressure are the freezing point of water and 1 atmosphere, respectively.